So I went through the book first. In my memory, the Zachman-Glow book was very, very good and accessible. But looking at it now, I'm thinking that you could actually explain this a lot better. And I was talking to Eric Borgesson about what kind of books they're at, what levels. So you tend to have really good, great books at the more advanced level, like this one. But you don't have at the kind of mid-level between undergraduate and master's, you don't really have a good book there. He gave me the name of one, so I'm going to send it out to you, but it's got some bad reviews on Amazon. So I'm wondering if this this book is probably the best book that we could have got, and despite its limitations. So I went through the book first. I'm going to explain that so you can see it in context, but then I'm going to just jump and show you why he's doing what he's doing, because that was part of the problem. As I was going through the book, I'm like, Calc 3, Calc 3, Calc 3, bizarre thing from Calc 3, another bizarre, it's like there was no connection to where this was headed. So I thought I'd go backwards, show you where it's used, and then flip the orders and show you the reasoning behind it, but not with all the gory details, kind of how he was showing and building it up. So bear with me here. The method that I'm going to show you today is called the method of characteristics, and it's the method that's used for first order differential PDEs that are quasi-linear. So these are sections 1 to 3 in chapter 2, but again, what I ended up doing is instead of going through details in the book, I went through some so you can kind of see how it fits in. I went to YouTube videos of Chris Tisdale, who I've known for, I think, almost 20 years. And I was really surprised to see these really fantastic lectures that he has online. He's really gifted at explaining these concepts geometrically. So I went to his YouTube site and kind of picked out the pieces I wanted to from there. And so you're welcome to go there. It's nice. So the book first defines a vector field. And a vector field symbolically is described as v of x, y, z is equal to a function of px, y, z as the first component, another function as a second component, and another function as a third component. And they have some restrictive properties that they added in on it that they describe in the book, that they want v to be non-vanishing. That means that none of the components are zero simultaneously, and that all these functions are at least C1 in the domain that we're discussing. So they kind of absolve themselves and say, whenever we talk about vector field, we mean that we have these extra restrictions on. And note that these are functions that go from R3 to R. So he provides some examples, like the constant vector field, and I attempted to draw this. That's my drawing. You're going to see the maple drawing in a second, and hurrah. He calls this the radial vector field, and you're going to see why when you see that picture drawn. It's really hard for at least myself to draw these things in 3 dimensions and see them. I bet Jimmy could draw it, actually, though. You're a 3D kind of person. And I wasn't going to draw that. Those are just 3 examples of, and of course on the third one, he's eliminating the z equals 0 line, because on the z equals 0 line, the function's not C1. So omega in the last case can't include the z-axis. So the plots are going to be on the next 3 pages. That's the first one. I thought I did a pretty decent job on the first one. So it's just constant vectors all going in the same direction, 1, 0, 0. And this is the radial one. So if you draw that, it looks like, so if you think of y equals x, they're kind of like diagonal lines, but they're all moving around, so they do look radial when you graph them all. And this is why he called them the radial vector field. And I think, did I do that twice? I did. I wanted to show you that last one. So maybe I'll send it to you by email so you can see it. That last one, if you graph it with too big a window, it freaks, the computer freaks. You really need a really small window so that you can see this, because it grows and blows up by the z-axis. So you have some freaky behavior. Here he's all of a sudden shifting gears and talking about integral curves, and we did cover integral curves in Calc 3. Calc 3, if you recall, was kind of a jumble of topics. So you start out with polar coordinates and then you move to path integrals, and then from there you move to, I think, tangent planes, and then somewhere in the middle of that you have the volumes with triple integrals. So you have all these different topics, and they appear to have no connection whatsoever. Inside those mess of topics, you have integral curves. And actually, Calc 3 is the foundation for PDEs. And if some kind of umbrella was put on top of it, it would make more sense of what you were doing. But why I wanted to point out that this isn't a Calc 3 book is that you could pull this out. Probably when you took the class, you might have been similar to me and just going from one topic to the other saying, okay, formula, 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 pass. Formula, formula. You have the formula, you plug the right thing in, and then you forget about it until you see it reappear in a class like this. So there's pictures on page 26 to get an idea. They're paths of motion that follow the vector field. So you can actually see it moving along with the vector field. With the vector field, we have an associated system of ODEs. So if you recall, the P was the first component, and the Q was the second, and the R was the third. And you can parameterize these curves so that you consider the X to be a function of T, the Y to be a function of T, and the Z to be a function of T. And as he's explaining this, you're going, why? Why is he doing this? All of a sudden he has a system of ODEs. You'll see in a minute why he has that. So a solution to the system is called an integral curve of the vector field V. And these guys are all slopes of the tangent to the curve. So when you graph each one of these x, y, z coordinates, what you're going to get, if you graph the derivatives, you'll get a tangent to that curve. If you have, the reason this is important is if you have that it's an integral curve, then it must be represented by a system to the solution that's I have bracketed on the left. So this integral curve has something to do with the solution of a PDE. That's where it's connected. And all solutions that you can get from this system yield all of those integral curves at once. It's going to form a surface. You can imagine a bunch of curves coming together. You're going to get a surface, and that's referred to as the integral surface. So let's go back to this. You can start like putting one thing over the other. Like I put dy over dx, and you're not really supposed to say it this way, but cancel the dt's, and you can get a system here that has eliminated the t's. And you can get the dz dx also to eliminate, and all other combinations. So you can get many different equations set up from this system of equations. So you could get, for example, dy dz, for example. And if you cross multiply all these guys, what you'll find is you'll get a system of equalities that are all related to each other. And this is actually how you get what's called the characteristic curve. And right about now, I'm thinking to myself, I know this has something to do with the solution, but I need to know the punchline. I can't just keep going on here. So I wanted to show you an example so this makes sense, so you can see a real example. This was the radial curves that I showed you initially with P equal to x, Q equal to y, and R equal to z. And I can actually solve for one in terms of the other. That's the point that he's trying to show you, that if you have these equations, then you can actually solve them using, in this case, it's just integration. Sometimes you'll have to use separation of variables, which is why we learn separation of variables. So I can solve this system. So if I set these two equal to each other, I'll get natural log, the integral of 1 over x is natural log x, and the integral of 1 over y is natural log y, and I'll get e to the natural log x is e to the natural log y plus c, and x is equal to y times c1, and what I get from that is x divided by y turns out to be a constant. And I don't have to go through the work again. You can do the same analysis and show that z over x gives you another constant, c2. It turns out that the left sides of these guys, the x over y and the z over x, turn out to be the first integrals of v equals x, y, z. So that's what he means by a first integral. Then he rephrases this as a surface. And here's your PDE starting to show up. So if you have a surface and it has this property that you have this equation that satisfies it, we talked about surfaces last time, right? So if you have this relationship here, then u of x comma y comma t is a first integral of this v. So there's a connection between the solution to this and the original vector field v. So what do we mean by all this? Here's the formal definition of first integral. So a function u that's C1 where omega is contained in R3 is called the first integral of the vector field if at each point x, y, z belonging to omega, v is orthogonal to the gradient of u. Go back and look at this. You can rephrase this entire thing as a dot product. So that the dot product is equal to 0 means those two vectors are going to be orthogonal. So there I've written it more like a dot product. And he talks about intersections of surfaces. So you can actually, as you recall, if you have a curve can be considered as the intersection of two surfaces. So I could have two surfaces and then have them intersect in the form of one of these integral curves. And he has a fantastic picture in the book right around this section. I think it's on page 26, around there. And then I think right here, I wanted to see the connection made from the top down, not from the bottom up. So what he's trying to tell you is that the general solution of this guy is what we're looking for. And what we're going to seek is a function that is equal to a constant, a level surface that satisfies that above equation. And the equation that we're going to start out with is a quasi-linear first order partial differential equation. So you're getting the solution method to that equation. And we call it quasi-linear because if these were all constants out in front, then it would be completely linear. But because these guys are functions out in front of the ux and uy and uz, we call it quasi-linear. And it's first order because all the derivatives are only first derivatives.